Hello guys, so welcome back to our VHDL lessons. So we're gonna explore in this video the second design for the second way of designing or coding the 3 by 8 decoder with enable. So we see in the first recording the primitive design with no enable signal or something, which is basically a description for the gates inside this design. And it is just like what we did with the 2 by 4 decoder. We explored the two designs, one for the gates, or that it describes basically the gates and the connections of the circuit, the digital circuit itself, and the other one was which was using the select when statement in VHDL, in which you can describe basically the truth table. And here is, the second way of describing or coding the 3 by 8 decoder using the truth table description of the design. So, I just compacted the three inputs X, Y, and Z in one variable called W. And this W is basically 3 bits. So basically X is Y of Z, is W of 0, Y is W of 1, and basically Z is W of 2. Okay, this is basically what I meant by compacting them. Of course, this will be better in the test bench, because you can use now the radix as unsigned, and you can see instead of the bits you can see a number, and of course, because these are really relatively easy numbers to imagine. Then we have here the enable input. Then here is the output. So basically we have 8 outputs, because with 3 bits you can have 8 minimum terms. Minimum term 0, 1, 2 until 7. I call them all D. So D is basically combining or compacting all the 8 outputs into one variable. So basically, for example, D0 is basically D of 0, D1 is basically D of 1 until, and D2, for example, D of 2 until, until D7, is basically, is basically D of 7 as well. Okay, that's basically, let's go now to the design. As I said, we need a signal to select upon each based on its value. And this signal should combine basically the input and the enable, because if the enable is 0, all the outputs will be 0. They will not follow the decoder logic anymore. I mean, they will not represent the minimum term of the input. Okay, so that's what I have basically do here. So here we have a signal called WEN, which basically concatenating the W and EN. The W is a vector, 3 bits, and EN is just 1 bit. So basically we have 4 bits. That's why I defined it 3 down to 0, 4 bits, 3, 2, 1, 0. Okay, and then the output D will be, will take a value, different value based on the concatenated signal WEN. Okay, so D will be 1 and then 7 zeros. Okay, this is 1, 7 zeros. When basically X, Y, Z, all of them are zeros, because this is basically minimum term is 0, but the enable must be 1 at that time. So this is basically 3 zeros, then 1. This is the bit for the enable, the 1, and here is the bit for X, Y, and Z. D will be zeros and 6 zeros here. Okay, when this is basically minimum term 1, which is 0, 0, 1, X 0, Y 0, and Z is 1. So here is X 0, Y 0, and Z is 1. Then the enable also must be 1. And you can continue with the same flow until, minimum term 7, the 8th minimum term number 7. Okay, in which, the least significant bit here would be 1, which is D7 basically. Okay, and again, I ordered them in this way: D0, D1, D2. You can do the opposite. That's fine. Okay, and this is happening when X, Y, and Z, all of them are 1s, and of course the enable is 1. Then, whenever the enable is 0, whatever X, Y, and Z is, then the output will be 0. And basically with the select to win statement in VHDL, you must add this when others at the end. You must do it. It's a default. Okay, so let's now run the simulation. Here is basically test. First, let's explore the test bench. It should also be easy. So in the test bench here we have very similar to the test bench of the 2x4 second design for the decoder. But now W is 2 down to 0, 3 bits, and D is 8 bits, 7 down to 0. Okay. Then I define 3 signals to be connected to these 3 input outputs. Then I instantiate a design, my design, and connect these signals to these input outputs. Then here I'm giving values to these signals. So remember, the enable signal just take 0 or 1. So here is the loop on a standard. So I define here I as standard logic, okay, which will loop over 0 to, of course, it's just 2 signals, 2 iterations. But then J, which will be assigned to Wn, this is basically 8 values, 0, 1, 2, 3, 4, 5, 6, 7. These are 8 values. So J here will iterate from 0 to 7. And this is the old way that we used to do, okay? Then I will assign J to Wn. And of course, as I said, to use such a conversion, this is basically a conversion from constant to standard logic vector. We must, include this library. You can do it, by the way, as like this. It will be for J in standard logic vector range 0, 0, 0 until or 2, 1, 1, 1 loop. Then you write whatever you want. Okay. And of course, at that time, Wn will be, equal to J directly without using this long, statement. Okay, guys, this is basically the test bench. Here is the running of the test bench. Okay. So whenever the enable is 0, and of course I'm here using the radix unsigned. Okay, this radix here. So I can, look at the signals as numbers, which is really easy. So whenever the input, let's go back to the truth table here, because basically this is a truth table. When select state, when a statement is basically a way to represent the truth table, the design using truth table. So when the input enable is 0, whatever the XYZ is, whatever W is, then the output will be 0. Look, it's 0 all the time. If you want to check, if we uncompress it like this, look, here is 8 zeros, 8 zeros, 8 zeros. This is basically D7 to D0 or D, until here also 8 zeros. Okay, good. Then enable become 1. So the circuit is enabled. So now the circuit will do its job. It will look at the input XYZ or W now, and based on the input, it will give or it will represent the corresponding minimum term. Okay. So for example, when XYZ is zeros, all of them are zeros. This is minimum term is 0. So minimum term is 0 means 1, 0, 0, 0, 0, 0, 0, 0. 1 and 7 zeros. This one is basically 2 to the power of 7. 2 to the power of 7 is 128. Okay. Or you can look at the individual signals like this. Look at the individual signals here. So 1, then all other signals are zeros. Okay, that's basically enlarge it, yes. Then when X equal to 0, Y equal to 0, Z equal to 1, this is basically minimum term 1, which is 0, 1, then 6 zeros, or 2 to the power of 6, which is 64. 64. Then 32, 16, it's really easy. Or you can look at the pattern like a diagonal as usual. Okay, guys, that was basically the homework solution. Hope it was clear for you. Thank you very much for watching this video and see you in the next video. Bye-bye.